Intermediate Algebra, Section 9.4, Properties of Logarithmic Functions. Logarithmic functions are important in many applications and in more advanced mathematics. We now establish some basic properties that are useful in manipulating expressions involving logarithms. As their proofs reveal, the properties of logarithms are related to the properties of exponents. And let's set down the properties and then put them to use with some examples. This first property is called the product rule, and it's related to the product rule of exponents. When you have common bases multiplied together, you add your exponents. So the property says if you have log base A of a product, we'll call it Mn, it's equivalent to log base A of M plus log base A of N. The next property is related to the power rule for exponents. A to the m raised to the n is equal to a to the mn. We multiply exponents. And the power rule for logarithms then looks like this. Log base a of m to the p power is equal to p times the log base a of m. That exponent on this quantity turns into the coefficient. The quotient rule for properties of logarithms has a similar basis from the exponents. When we have common bases divided, we subtract exponents, and you'll see a similarity here with the logarithmic quotient rule. If we have log base a of m over n, the quantity or the quotient, it's equivalent to log base a of the numerator minus log base a of the denominator. Logarithm of a base to an exponent is the following. If we have log base a of a to the k, and we saw this earlier when we defined logarithms, it is equal to k. And this follows directly from that definition, as I said. Some other properties that we skirted around without formally identifying them by name in the last section are the following. We have principles of exponential equality, which states the following. If a to the m equals a to the n, common bases equal to one another, then we can assume that those exponents must be equal to one another. And this is known as the principles of exponential equality. Principles of logarithmic equality state that if we have log base b of m equal to log base b of n, same bases, log of a same quantity, then m must equal n. Two other properties that go along with logarithms don't have a specific name as the following. If you have log base a of a, it's equal to 1, and we can verify that by translating this into an exponential form. Similarly, if we have log base a of 1, it's equal to 0, and we can see that in practice as well. So let's put these logarithmic rules into play. And in these first examples, they're asking us to express as an equivalent expression of sum or difference or product of logarithms. So we have the log of a product, which we can separate into log of sums. We use the same base, so we have a product. So this would be equivalent to log base 2 of a plus log base 2 of the second factor, which is b. This is using the product rule for logarithms. We have a similar situation in the next problem where we're taking log base b of a product. To express this as an equivalent expression, we'll use the product rule again. So it will be log base b of the first factor plus log base b of the second factor. In this third example, we're taking the log of a quotient, so we'll use our quotient rule, which says use the same base, log base 6, of the numerator minus log base 6 of the denominator. In this problem, we're taking the log of a quantity raised to a power. Here we'll use our power rule, and our instructions are asking us to write an equivalent expression for a sum, a difference, or a product of logarithms. And here's where the product comes in. When you are taking the log of something raised to a power, that exponent comes out as the coefficient, so it's 9 times the log base 2 of b would be an equivalent expression. This may not look initially like the last one, but if we replace our radical with an equivalent exponential form, the square root of n would be n to the 1/2. Now we are taking the log of a quantity with an exponent. That exponent comes out as a coefficient 1/2 times the log base 7 of n for an equivalent expression. These next problems are very similar, only with less numbers. They're asking us to express as an equivalent expression using logs of x, y, and z. So initially here we're taking the log of a product. So we'll separate that into the log of the sum of those factors. And then this is a log of x, so I can't do any more with that. But the second quantity, because we have y to the second power, the 2 on the exponent can come out as a coefficient when we use our power rule of logarithms and say it's equivalent to 2 times the log base 6 of y. And you may have, once you get comfortable with these properties, have jumped right to this second simplified version. In the next one, we have log base a of the cube root of this quotient. So first, let's get rid of that radical to help us see what's going on. So we have y over z to the 4th power raised the whole quantity to the 1/3 power. To get rid of an exponent using the power rule, that will become our coefficient 1/3 times the log base a of this quotient, y over z to the 4th power. Simplifying further, we have 1/3 times the quantity. We have a quotient, and for a quotient, an equivalent expression would be to take the numerator minus the log, of course the base stays the same, of the denominator. And one step further, because we have this power or an exponent, it can come as the coefficient. So we have our log base a of y minus 4 times the log base a of z, which is an equivalent expression. And the only other thing perhaps would be to distribute the 1/3. And just to show that each of these terms is raised to, or should be multiplied by 1/3, is because of the fact it was the cube root of this quotient. It was that quotient raised to the 1/3. So distributively, each one of these logarithm terms has that coefficient of 1/3. So if we want to eliminate the parentheses, we'd have 1/3 times the first log. So we'd have 1/3 log base a of y, and then 1/3 times 4 would be negative 4/3 log base a of z. One last example, we have here log base 4 of a quotient. This one isn't quite as complicated. From the standpoint we don't have a power to deal with, we have a quotient. So using the quotient rule for logarithms, this will be log base 4 of the numerator minus log base 4 of the product yz. We don't have these separated because we have these two factors here in one logarithm, so we need to split that out. And we do have to be careful. This is a subtraction of this whole log. So when we replace the log of a product with the log of the sum of each one of those factors, it's subtraction of that whole expression. So it's not only log base 4 of y that's being subtracted, but also log base 4 of the second factor. These two are equivalent to the log of the product, and if we want to eliminate parentheses, we're subtracting a quantity, so it's not only minus log base 4 of y, it will also be the subtraction of that third log there. So minus log base 4 of y minus a log base 4 of z.